third order. And we call the second derivative a force constant, calling it dI beta, which is the same thing as any questions on this? We discussed some properties. It's fine. Then we said we can write Newton equations. Let's say in the alpha direction as these forces. So it will be a sum over the alpha beta times u j beta. We gave an ansatz for the displacement. With an amplitude, which is the same thing as if you write the space dependence completely. And using this displacement and the Newton equation, we also derive the dynamical matrix. Oops, let me make it squared. Now I should check the signs. Beta R. This is for monatomic lattice. And we are linking movement in x with the movement in other directions. We call this dynamical matrix. And specifying either force constants or dynamical matrix, you completely define the system. We solved it in the case of 1D chain. We obtained the was it? And we plotted the dispersion in the first Rubin zone. And here it's linear. Goes as a sine up to the value of 2d0 over n. We discussed the limit when k goes to 0 as a long wavelength limit. The wavelengths of the audible sound to humans are between a few millimeters, like 20 something, up to 17 meters. So this is the sound that we can hear. And what I didn't do yesterday, because I forgot, is to actually say a few words about displacements between different cells. So, the displacement in a cell n plus 1, versus displacement in a cell before. In what relationship they are? We can plug in the value. Now, I don't care about the amplitude in the same direction. I will have ik n plus 1a over ik na. Okay? R is na. So I'm just looking at the relationship between displacements in two cells. So this is the atom n, the atom n plus 1. How they move. And this is equal to IKA. Fine. If K is 0, this is 1, and we can tell that is displacements between neighboring cells are the same. This is what we already said. We call it displacement of the center of mass motion, when all the atoms move together. We have only one mass, they move by the same amount in every cell. This is typical for the acoustic wave, for the small frequency, for the sound wave. What happens at the zone edge? We find that they move in the opposite direction. So here, the zone edge movement of the acoustic mode is specified by the motion opposite to each other. So we have this guy is moving here, this guy is moving opposite in the same, by the same amplitude. This guy is moving here and so on. We have only one mass. This is still inner chain. Today we'll go a step further. And then I'll give you quite a bit of homework, I'm afraid, for Thursday. I hope you can make it, as we can do on the blackboard during the lecture. Because it's something that you can really derive yourself, at least up to a point. And then we discuss together. And what we derived is one normal mode. I don't think I used these words yesterday. It's a normal mode of motion with a specific frequency, which depends on the number of degrees of freedom, but we will discuss it today a bit more in a slightly bit more complicated case. So, any questions on this? All clear, all easy? Great. Today we continue looking for dispersion relations and normal modes in a slightly bit more complicated case containing two atoms in a unit cell. So, still 1D. How did they call it? I don't even know how I call it. Wow. So we have a linear chain, a chain, and the unit cells. And in each of them, we have two different atoms. So we have a basis here of two atoms. Atom 1 and atom 2. Or I can call it a cell n, n plus 1, n minus 1. In principle, they should have two different masses.
Yes.
But for the time being, I'll simplify the thing. And I'll make you homework to derive it for two different masses. Because somebody wanted to know how it works. I'm joking. So I will assume that, but we will analyze it next on Thursday, is the same. But what is different is the force constant between them. Within the cell, within one unit cell, let's say they have a very strong coupling. I'll draw it like this. With a strong, with a large force constant. I think it's intuitive to denote like this, tight spring. And between the cells, it's much weaker. So almost flat spring. I'm just inventing symbols to be more intuitive, because what I used before wasn't so intuitive and students were forgetting what I'm using, what it means. Now I'd like to take a minute to go back to some real physical situation that this system can describe. So this would be a molecular crystal. In this case, for molecular crystals, also called van der Waals crystals, you don't really have a charge like in ionic crystals, or even in the covalent bonds or something. You have a closed shell. The typical thing, what you start with when you talk about molecular crystals, are noble gases. Atoms of neon, argon, xenon. They are completely filled, they have completely filled outer shell, closed shell. They are happy as they are. So, well, imagine two of such atoms. However, it is still possible, and then in the gas state, at room temperature and ambient pressure. However, it is possible to crystallize them. So they can bind. How it happens? Like as time average, each of these atoms, it can be a molecule, but it's simpler to talk about two neon atoms or two argon atoms, don't have a dipole moment. Time average of dipole moment is 0 for each of them. However, one electron, the furthest one from the core, can oscillate, and instantaneously it does create a dipole. Dipole of the form, this is the charge of electrons, or can be even more electrons. This is a very, very rough qualitative derivation, not very exact, but just hand waving to get to the dependence on the distance. And this oscillating dipole, instantaneous, is actually producing electric field, which, let me just say, depends as this dipole moment of atom 1 divided by r cubed. This is one of the basic results you derive probably at some point in E&M class. The atom 2 feels this field. It's a tiny field and oscillating in time. But however, it's enough to induce a dipole in atom 2. So, the dipole, I'm just putting the absolute values, will have induced dipole proportional to the electric field with a constant called polarizability. How easy is to polarize an atom or a matter in general. And therefore you can evaluate the interaction energy of two dipoles, as I'm not using any real units, so let me just keep writing like this. And P2 is equal alpha times the field, which is squared alpha 6th power. I wanted to arrive to this 6th power. This is the typical value of attraction, dependence on the pair distance for the attraction in van der Waals. I think I mentioned something yesterday. So you can write the interatomic potential in van der Waals as attractive part plus repulsive, which has to be stronger than this. The core repulsion cannot come closer than some value. And it's chosen to be 12, which is no real reason except it's easy to calculate. I think I mentioned yesterday. This is all a bit on the side. This is called Lennard-Jones, as you probably know. And this is one of the easiest things to calculate. It's well defined. You cannot do this so easily, the interatomic potential for metals. It's much more complicated. Here it's enough almost to sum over all the pairs, and you're fine. For covalent and metals, you need more complicated interactions. Okay, this just says that this is a dipolar interaction between noble gases, but also molecules or compounds covalently bound, like HCl, can actually form a crystal which is bound by van der Waals forces. Do you know an example of a molecular crystal? Just think. And atoms or molecules are bound by weak forces, dipolar, so that they don't have any ionic charge. They are neutral. They will just bind to other. Okay. The everyday example is ice. Ice forms a hexagonal crystal, I think, which melts at 273 Kelvin, as you know. They are all bound by dipolar forces. HCl, I think it melts at a bit higher temperature, 340 Kelvin. While noble gases, they melt, I think argon is around 70 Kelvin, and a huge pressure. Both you need to impose to visualize.
Hydrochloric acid?
Sorry?
Hydrochloric acid? Are you talking about hydrochloric acid?
Yeah, but not acid in a liquid, it's in a crystal state. So all of them can get a crystal state under some conditions. And then they form molecular crystal. I mean, for liquids, there are similar rules, but they are very, very short range. Now we're talking about something which forms a crystal. One cute example of a molecular crystal is a rock candy. I like to mention it. Maybe you know. It's crystals of sugar. You melt sugar in water, you put a stick, it crystallizes, and it creates a crystal structure. I mean, it's a crystal bound by weak van der Waals forces. And then some molecules, like N2, for example, they can also form a crystal, but it's not a dipolar force. It is quadruple, and it's much weaker than dipoles. Just to give information to have heard also that, to get some more. Any questions on this? We will continue with our derivation of phonons.
You know, I've understood the issue of the ice, but
The issue of, sorry?
I've understood the ice, that
Ice.
it's neutral and so on, because
Yes.
I'm seeing two positive charges and then
Yes.
the two negatives. But what about the N2?
N2, exactly. N2, what I told you here, for argon. You have two argon atoms. They don't have charges. They have instantaneous oscillating dipole moment.
So you take it like the nitrogen is
It's even worse.
to
It
the-
doesn't even have a dipolar moment. It will have only quadrupolar, which is weaker. So even worse. Or for example, the molecule like CO2, it doesn't have a dipolar moment because it's linear, it's in plane. I mean, you don't even do this.
Because
It's a
it's
covalent bond. So this guy has a very, it's very hard to make a crystal of it.
Yeah,
I have-
because I thought that the plus.
Do I have, it's 190 Kelvin, the melting temperature.
No, I thought that the plus and okay, the two minus comes from the valence of.
Okay, you shouldn't get confused. HCl also has charge. It's ionic. It's strongly bound within the molecule. But then I'm talking about the forces between molecules.
One molecule and the other.
I'm making a crystal out of it. So while it's really strongly bound, it makes the closed shell, it's very happy as a molecule, very stable. To make it bind into a crystal, the forces between different molecules are very big. And they are based on dipolar interactions or even lower quadrupolar interactions. I think N2 is very like 60, 70. Do I have it written? I think it's around, forgot, 70, 80 Kelvin that it's crystallizing or something. Very, very low temperature because it's very low binding energy.
So by just looking at maybe the chemical form of something, how do I know?
Well, you can estimate if it has dipolar moment or not, if it can create one or not. But yeah, there are some exceptions that you cannot easily analyze just by the formula. You have to know. For example, iodine, the molecule of I2, has quite a high melting temperature, although it's similar to N2. It's in particular nature, it's quite low in the column, periodic column, and actually has far electrons, so that they can distort a lot due to van der Waals forces. I mean, there are some things which are not easy to read off, but once you understand what's happening, once you see what's happening, you can explain it. Some things you can, of course, predict easily. Not everything. Fine. So we will continue with displacements. We have only x direction, so no need for alpha. We write it like that. And we have to now write two equations because we have two bodies, 1 and 2. I'll just use mass M. U1. Now this is the sum of all the force constants and displacements. I can write this times displacement U1, and so I should keep the index n for the cell because it will interact. I can make a trick which probably won't make you very happy. You know the acoustic rule, that D0 plus the first neighbors, we are in the limit of first neighbors, plus D of A plus the first neighbors, this should give 0. And then it gives me a negative force constant for D of A. I can say I can choose these guys to be negative, so they enter positively. It's a positive constant here. It's my choice. So, for this one, I'm in the cell N, interacts with atom 2 in the same cell. So, and this is the strong one, times U2 from the N, and the weak force constant with U2 from the cell before. And the same can be written for the atom 2. So this atom here interacts with atom 1 in the same cell via the strong force constant. And with the weak one, with the atom 1 from the cell +1. I will use the acoustic sum. Minus. So this 0 is the sum of these two. And I can also plug in my answers for the displacements. Please control me. It's easy to make a mistake at this point. M omega squared is now the index and here will be 1 or 2. One is equal to minus D0 is D strong plus D weak times U1N. Okay, let me write it omega T plus K and A. Sorry. Can you see this? I forgot the middle part. I don't want to cut it. I mean, I was going to do it all in one step, but it's better we go step by step. It was going to skip too many steps. U1. Plus D strong times U2 in the same cell and plus D weak U2 also. But not in the same cell, but one cell before. Oh. It's okay. Lots of writing, it's easy to make a mistake. And control me, I mean, I'll check in the end, but... And the other equation is very similar. 2 again T0, strong, force constant plus weak, U2, in the same cell, plus D strong, U1, in the same cell, U1, plus the cell in front. Okay. This is lots of writing, but it's not difficult, I hope. Okay, so what we go now, we cancel all the omega T parts, they are the same, and K and A parts. The same here. And we can also change the sign, multiplying by -1. minus first one. I divided by E on the I omega t plus K and A and multiply by minus 1. And omega square. This is equal. Minus T strong U1 minus T weak. Okay. Now I can write the second one, putting the U1 first, just to write the matrix easier. So U1 is minus the strong plus U1 plus it's the same thing, I just could change the order. And now where can I write the matrix? Maybe there.
Excuse me.
Yes.
There is a factor of e to the power ik.
Ah, you're right.
In the
Here, this one, I forgot. Yeah. Good. That guy will cause us lots of trouble. It would be nice to get rid of it. Any other mistakes you found? We might still. Okay, so I have a matrix. I'm writing the first one. U1, next to U1 is the strong plus the weak. And next to U2 is minus the strong plus the weak E minus IKA. Okay. Here is minus the strong plus the weak E IKA. Strong plus the weak. Don't have my space. And it's equal to m omega square. Can you see? I really squeeze them. Okay. Now all we have to do is solve this determinant. We'll solve it to get the eigenvalues. Let's go case by case. I don't like much this factor here. It's complicating things. So let's go in the case k equals 0. So I have a much simpler matrix. The plus the straight minus the plus the straight minus strong plus weak and the strong plus the weak. So it is like A minus A minus A. I never know it by heart. I could equals A squared. Let me just write because 1 is 0. This is for sure. Omega 2, I will copy the solution not to make a mistake, is 2 plus the weak over M. And let's somewhere start plotting our solution. Oops.
Excuse me.
Yes.
What are we really solving for? Are we solving for the displacements?
We are solving for the frequency. This is the eigenvalue. We want to find dispersion relation. It's kind of similar to what we were doing before, energy dispersion versus K. Now we are solving for frequency dispersion or dispersion versus K. Actually, I wanted to mention in many books they use a rule that for energy they use K, for the phonons they use Q vector to differentiate between. So it's right away clear. Ashcroft is not using it, so I kind of keep it K.
Because I'm thinking of a system of linear equations whereby even the solution matrix, do we know the U1 bar?
Okay, we will also find the eigenvectors. This is the eigenvector. We will express one, so you get 1, 1. They are equal or they are opposite. This is a normal eigenvalue equation. So we have to find omega and eigenvector. So, at omega, at k equals 0, we have two solutions. At omega 0, and a higher value to the strong plus the weak over m. Now we are getting a different mode. So at the gamma point, it can oscillate, vibrate with these two frequencies. So there are two modes. Obviously, there have to be two modes here. And in the end, what happens most often, it's a combination of the two in nature. Okay. Second case, zone boundary. That's also an easy case. Minus is strong.
Excuse me.
Yes?
There's something I'm not understanding.
Tell me.
You were saying we are looking for omega. So
As a function of k.
Yes, but you are using two equations to look for one unknown.
Also eigenvectors. I will express also eigenvectors.
Eigenvectors?
I want to find eigenvectors. And
But
there are two values which are unknown here. This is one, this is two unknown. But I don't care to know them absolutely, both of them. I just want a relation between them. So here it's actually one unknown if you want. U1 can be expressed with U2. Okay, and the strong plus the weak. So this is A, B, B, A. I'll copy the solution not to mess up. Omega 1 is to the weak of M. And omega is to D strong over M. Also at the zone edge, I have two values. Which one I plot higher?
D plus omega 2.
Omega 2.
Omega 2. It should be a bit lower than this one. So far everything was kind of smooth, but we don't have our dispersion relation. We have the beginning and the end. So I will not solve it for any k. I will just go now to the limit of small k to see what happens in the limit of small k. Okay. For that, I can actually expand this exponential. Then what matrix do we have? Here we have strong plus D minus times 1 plus I Ka minus Ka squared. Here we have minus D strong plus D weak. No, here it's minus IKS. Minus. Strong plus D weak. To make things slightly easier, I will call this A, this B, and then this is the B conjugate. Difference being in minus IKA here and here plus IKA. Here it's A. And then the eigenvalue equation will be A minus omega squared minus absolute 0. So I have to find the modulus of B. Maybe I start here because it will take some writing and I want to keep some things here. The modulus of B will be a square root. Now I'm bound to make a mistake, please control me. the real part is this, this, and this. I can disregard the sign because I care about the modules. So this sign I don't write. T minus T minus check to write in the same way because I won't be able to check
I think
solution.
that has to be this square.
Sorry?
Then that can be this square. And that's with this square.
So it is here plus a square of 2 times 3b squared. Is it correct? Yeah, okay. It seems to be correct. Okay. And now I will take this out. This is the a part. I want to express this b as a times something. That way it's easier to solve. I'm factoring out t strong plus dv. So this will be 1 minus v weak ka by 2 omega is plus k a squared d weak squared 2 times d strong plus d weak. Okay, and now I continue writing here just to use space better. Now I can expand this polynomial as 1 minus 2 times second power 2 times this, which cancels with these 2, minus, I can write it d small k a squared 2 of d strong plus d small plus ka squared d small over 2 d. This should be squared. D strong plus d weak squared. And then I can write this as 1 minus and put together all the dependence on t squared. All that I have here is 2d minus not anymore 2 d strong plus d weak plus can be also a square out d weak or 2 d strong plus d weak squared. for the expansion of the square root, 1 minus epsilon, square root of that is equal as 1 minus 1/2 epsilon. Maybe here. It is equal to strong plus the weak times 1 minus 1/2. Let's put k square, a half, and then some constant. This is constant. Finite constant, but k small. Good. And from here we could express the two eigenvalues. Omega 1 squared is a plus absolute of b, and omega 2 is a minus the absolute of b. So what do we have? This is equal the strong plus the weak plus this. Let's call it all like some C. Here. Just think something is strange. Yeah, here it's minus. Huh. Okay. I skipped steps, so please. Okay. I really made a mess now. Let's go from the beginning. Just correct the first thing. Plus the weak. This is A. Plus strong plus the weak times 1 minus k squared c, which is then equal to 2 minus the strong plus the weak okay. Survived. So this is squared, no? Yes. So omega is proportional to k. So again we are getting the linear behavior. All this pain to get something which is not so complicated. By the way, you notice that these phonon dispersions are symmetric. Omega of k is equal omega minus k. It's reflecting the symmetries of the Brillouin zone. And what we have here, we will start from this value, which is exactly this one. This is all missing an m. It will start from here and will very slowly decrease as the square root of a minus k squared going flat, going down. So this is how much we derived. This is it. We didn't derive more. But if you plot the function in any plotter, you will be able to then connect. Not very symmetric, but so we kind of cheated a bit to plot the full dispersion. We see there are two modes. There is a gap, and this gap in phonons is around, well, it's called, it can be excited by infrared light. This is the which is around up to 1 eV roughly. And below maybe 0.2, I'm not sure. Up to 1 eV roughly. And this is a typical gap. And actually this kind of excitation gives name also to the higher mode. We know this is called acoustic mode because of the sound wave for k going to 0. But the higher one is called optical mode. And here again, we have the limit k going to 0. Yes.
Regarding the gap, like phone frequencies corresponding to the gap cannot occur.
Cannot occur.
But what is this infrared light excitation that you're talking about?
I mean, okay, the gap is of this amount that you can actually excite from. But okay, I'm not talking about it. This is just a mention on the side. Okay, I will come to why optical also. There is a good reason for this when we discuss the displacements. Maybe before that, we can talk about the number of modes. So we can say number of dimensions, number of atoms in base, and number of modes. So I will come yet still to optical a bit. We derived yesterday a case of monatomic linear chain. Dimension is 1, and 1 atom in base. And we got 1 mode. Today we are still in 1 dimension, but we have 2 atoms in base, and we get 2 modes. If you had a crystal, a cubic crystal, dimension of 3, with 1 atom in base, a simple one, you would have 3 modes. They would be all acoustic. Yeah, maybe I shouldn't say first. Because optical modes can occur only if you have more than 1 atom in the base. It will be more clear in a second when I discuss the displacement. So what am I concluding? The number of modes, we don't have enough cases that you can conclude it yourself. That the number of modes actually corresponds to the number of degrees of freedom in the system. So, number of modes total is equal number of dimensions times number of atoms in base. And tell me, how many acoustic modes will a crystal have? Acoustic. How many acoustic modes can a crystal have?
Depends on the number of degrees of freedom.
Partially true. Huh? What is acoustic mode? It's the easiest to differentiate from this behavior at zero frequency for high long wavelengths. When you have a center of mass displacement.
I think one. Because
So you can displace all atoms in 1D along.
okay, three. Number of dimensions.
Good. It depends on the number of dimensions. So number of acoustic modes,
Okay, I'll just do that one.
because it shows how many center of mass
Degree of
degrees of
freedom.
freedom you can have. Number of acoustic modes is n dimension. And then the number of optical modes
Depends on the
yeah, but you know the
Degree of
total
freedom.
number?
Yeah, degree of freedom minus.
It has to be the difference. So it's equal, well, how to write the whole thing? Number of dimensions times number of atoms per cell minus n dimensions. Tell me one example when you will have more optical modes than acoustic modes.
Sorry?
Tell me one example when you will have more optical modes than acoustic modes.
If you have more than 2 atoms sitting
In a single dimension.
Everybody sees that? Yes. Confident, yes.
Yes.
Good. Now we can remove this. Oops, maybe I shouldn't have removed it. Yeah, I realized I should. Because I want to discuss the eigenvalues, what William was asking, for the limiting cases. Well, we'll have to use the notes. You have the matrix for k equals 0 case, no? Eigenvalues. For k equals 0. So we have to look back into the matrix. And when you put omega equals 0, now you're putting notes because I don't want to write the whole thing again, you will get that U1 is equal to U2. And when for the omega equal to the strong plus V, okay, U1 is minus U2. So for the sound wave, we produce again the same result, that all the atoms are moving with the same displacement. However, for the optical mode, you get a different behavior. Maybe I can draw it somewhere. I'll try, but it's not easy to draw these things. So the case, let me see, this is the unit cell. This is the equilibrium position of the second atom in the unit cell. And K equals 0 optical, and small k, let's say small k acoustic. You will have atoms moving in phase, the big one and small one. What I'm completely disregarding here is that displacement actually do depend on the mass. Here we have equal mass and they have the same displacement, so we are happy as time being. So they have the same displacement. Okay, this is easy. Now the optical mode at k equals 0 indicates they're moving in the opposite direction by the same amplitude. So it goes, one goes here, and this guy goes here. Is this okay? Everybody's following?
Yes,
Yes.
Yes. So this guy goes here. This is, of course, multiplied by some 100 times what I'm showing, the relative displacements. They're much smaller. I have to, otherwise you don't see anything if I draw the so what you have in the optical mode, two atoms coming closer and further from each other. It's an oscillating dipole. So this and the fact of this gap give the name of the optical mode. So at the zone boundary, the solutions are, what do they call omega 1? Complicated to look. Omega 1 is the weak one. It's acoustic. Omega 1. U2 and omega 2. But we can do again the ratio of the displacement in the nearby cells. Now, if we do the same thing as we did in the beginning, U1, let's say, of n plus 1, U1 in n. And while here, in each cell they move the same, both for the acoustic and the optical, in each cell the same, but not in the cell. In the cell is the opposite. For the zone boundary behavior, you will find that it's changing. When you put pi over a, you get -1. So each cell has the opposite motion. I'll try to draw it. I'm not sure I'll be successful. Okay. So acoustic one, it's a bit easier. So they move by the same amount. But in each cell it opposes the direction. again. And the optical one. But in the next cell, it goes in the other direction. Here it goes again inside. And so on. Now let me give you homework for Thursday. Do you have any other homeworks for Thursday? I think I got the answer. Okay, let's say who manages. I'm not grading it. If you can, it's useful. We'll do it in the class, but it's something. So homework number 1 is to derive dispersion relation, or maybe even dynamical matrix, for the case 2 masses. So again, the linear 2 masses. Well, 2 atoms, let's call it 2 atoms per cell in the base, and M1 is different than M2. For that, I give you an ansatz from which it follows everything. That U1 is equal to U1 amplitude, depending on the mass one, and okay, NA. And the U2 will depend on the mass 2. But the simplification, let's put N also, that the 2 spring constants are the same, to make it simpler. So there is no more anymore the strong and the weak, they are the same. So you get a simplification here. Something like sodium chloride or something. But in 1D. You try. I don't think it's too difficult. You have all the tools just to see what dispersions you will get. But I still might already give now some of the solutions. Okay.
In this case, we will get the complete solution or just boundary solution?
Well, not, but I mean, you just do as much as you can. Well, make it a k equals 0 and pi away. I mean, that's fine. Just to see the frequencies.
The solution is the same. Solution will be the same. You just change the masses.
No, it cannot be the same. Well, but how will they enter?
I say it becomes the difference in the masses.
Yeah, sure. But here you have 2 springs. You have only one force constant, so it's not so obvious to me. I'm so quick it is for you. And now let's consider limits. First one I put was, okay, if the strong force constant is much, much stronger than the weak one. What do you get? Just look at this picture. These guys are strongly bound to each other.
Only acoustic. Oh no.
Well, and they are decoupled. This D weak is very low. So this guy goes down. Oh, I can plot it again. is the limit. This is the limit of not interacting molecules, decoupled. Let's say at some high temperature you may get it. So you have a collection of independent molecules. Okay, this is the first limit. The second limit, what happens if they're the same? This should be simpler, no? We have okay, let me draw the situation. So now they're the same. Oops, one is much longer. Okay, and what do I get? Oh. Uffa. Maybe I should draw again. Giving up. I can spend here 20 minutes drawing it. Okay. They're the same springs, spring constants, the same masses. But you remember last time we derived the same springs, the same masses, 1D. We derived it like this. Why don't we have the same?
Because we have two atoms.
You're too fast. I wanted everyone to think. So Nika gave the answer. Did you hear the answer? Yeah. We don't have the same because in this case, our unit cell is twice longer. If you have the same masses and the same springs, it's twice the unit cell of yesterday. And you have folding of phonon bands, just as we had the folding of the energy bands. It's the same thing. Okay? And I will just take like a few minutes to discuss let me also give you the homework number 2. Let's see what you can do. Homework number 2 is a bit trickier actually. The first one is straightforward. You go and derive and you will reach it. Number 2 is a bit trickier. Still 1D chain, 1 atom per cell. But also second neighbors. Take into account also second neighbors. Well, it's not difficult to do technically. You should also derive the conditions of stability.
Is it second neighbor with respect to?
The first and second. So you take
With respect to n or both n plus 1, n plus 2?
for each of them you take second neighbors.
Okay, each
First,
of them.
of course, I mean, you cannot.
Then the second neighbor will never end.
Neighbors is plural. And taking into account the conditions of stability. And then we will discuss. What does it mean, condition of stability? That was my question. Here, what we did so far, we always had positive omegas frequencies. So try to keep it so. And you will see that depending on the force constants, on the strength of the force constants, you might go to actually negative frequencies.
So we will have to take different force constant for first neighbor and second
Exactly.
neighbor.
Exactly. You will have force constants, the first neighbor and the second neighbor, and you'll have to put some conditions on them not to have negative frequencies. I suggest you try to do it on your own. I mean, there are notes from before you can copy, but it's not the point that you have it correctly solved. It's just to think and to come to as far as you can, and then you finish in the class. It's not graded, it's not. It's just to be able to, I mean, that way you can get the most of the class, but I know if you cannot, if you don't have time, you cannot do it. Okay, good. Now what I wanted to mention still, is the displacement in a general case. What is, rarely you will have a system moving in a single mode or mode. It will be a combination of the two modes or n mode available. So what you will have in general, it's a superposition mode. So in this case, we could write U1 alpha will be equal to U alpha 1 So this is the first mode and the second mode. So in the case we have, there will be, for some case, here, there will be two different frequencies. And the system will actually, in general case, have a combine both of these displacements superposed. And in the harmonic approximation, it is assumed that the movement in each of the modes is totally independent of the motion in the other modes. This is harmonic approximation. It's a consequence of that. It is not quite so in reality, but this is the approximation that we take. And as we are always in one dimension, all the problems so far, and even the next time in 1D, I'll give you results for 3D, because we cannot go and solve everything. We'll have for the homework. I'll give you homework on Thursday on phonons, more homework. So in 3D, what you can have, so far we had, in 1D you can have only one type of motion along the chain. No? But okay, before we come to 3D, let me just draw in 2D what you can have. And let's say we propagate the wave in kx. And what we had so far, the atoms were moving along kx. But in reality, it doesn't have to be so. We just didn't have an example in higher dimension. They can as well move perpendicular to the direction of propagation. It's possible if you have more than one dimension, so they can move. And depending on this, there are two types of modes. What we had so far, when the propagation is, direction of propagation of the phone is parallel to the displacement, is called longitudinal mode. Maybe I can draw one more case here and keep it longitudinal. And then this mode can be both acoustic and optic, depending if they move in phase or out of phase. And the other one, where the displacements are perpendicular to the direction of propagation, it's called transverse. So in 2D case, we can have one type, optical and acoustic with one atom per cell. And how many transverse modes? Yeah. So let me say in 3D what you will have. And 2 atoms per cell. Now here it was confusing because I drew only one atom per cell, so I was talking about optical, talking in general for any. So, good. How many? Let's say this is the zone boundary. I'm not even saying what kind of cell it is. 2 atoms per cell and 3D. How many acoustic modes I will have? The motion of central mass, as many as directions in space. So, okay. So they're all acoustic modes. I will put a symbol A. But are they transverse or longitudinal in 3D? We have a given K. I chose a K. It's given. I can call it Kx, but it's not important. For any given K, how many transfers can I have? Or how many longitudinal?
Longitudinal one along K.
Yeah, because you chose the K, and only one can move along that. And this one normally has a higher frequency than the transverse ones. So you can imagine that along the K, they are moving all in phase, but it can be up or down and left or right. And how many optical modes?
3.
So the total one is 2 times 3, 6.
3.
So we have 3 optical.
Excuse me, I think I was not paying attention, but a transverse mode has, each transverse mode has to be perpendicular to the longitudinal mode and perpendicular to themselves.
What do you mean to themselves?
Like if we have 2 transverse mode in this case.
Okay, yes, in that case.
So I was just,
These
because
are the
then
modes.
we could have like
But you can
infinitely
have a combination of that. These are the modes which will be fine. I can go with XYZ, but I don't have to. I can
So
go.
this will be perpendicular to longitudinal and also perpendicular to themselves.
Yeah, normally it's defined that way, yes.
Okay. Otherwise,
Otherwise
in
they
a
are
plane you can have
dependent.
infinitely many transverse modes, like possibilities. Because if it's like this,
In
like
a plane, no. In 2D, no.
No, ma'am. In a plane,
3D.
in a 3D.
Yeah, okay.
Let's say
exactly, true.
if we have
I
a
agree.
longitudinal mode this way, any.
But then they are
vector in this-
dependent of each other. You can express one with
Okay, okay.
so there is no point. They're not
They have
modes.
they have to be orthogonal.
I mean, to have, you will say I have two different ones. And, oh, not my drawing day today.
So, excuse me, can you please explain how you came to the conclusion that we have two transverse and one longitudinal?
Okay, in 3D,
Yes, yes, yes.
how many acoustic modes can you have?
The number of dimensions, 3.
That's clear, so there must be 3 of them. Then you have, now imagine a cubic crystal, well, a brilliant zone,
Yes.
and along Kx, you will have, no, well, you have in primitive cell information.
Oh.
You understand?
Yes, I
Along
understand.
one direction, they
Yes,
can move
yes,
in
yes.
only one way, in the alpha mode.
Yes, yes, yes. I understand.
It's just, the names are complicated. It sounds like, but when you understand, it's really
Yeah, it's fine.
nothing smart. I mean, and optical, again, how many transfers, how many?
Two transfers again.
They don't have to be always spotted the same way. That can depend. But this is the normal way to call them. The order can change. That's not. And then I wanted to, yeah, indicate a bit how it moves. So let's say in a transverse mode you have two types of two atoms per cell. How they will move? It will be atom A, and then atom B, atom B, atom. Okay. I'm showing transverse displacements, but as you can notice, I'm not plotting the same displacement for A and B atoms because they don't have to have the same mass. I gave you the answer that a displacement is proportional to the mass of the atom. And it makes sense. The heavier atom will move less, the lighter one will move more. So here the atom in the amplitude, and here the atom A is obviously lighter, moves more. And this is the transverse mode. Along one direction, let's say. Optical, yeah. Okay, and then longitudinal one. This is a longitudinal optical mode. And let's see what we have for the acoustic. Okay. And actually it'll be a different curve. It's B, A, B, A, B, A, B, A. This is acoustic. A longitudinal. Sorry, transverse. Acoustic. And then on. Longitudinal acoustic. So, I mean, we didn't derive it. We'll do one exercise in 2D, but it's good to have the idea what is what, that you can solve the exercise when I give it to you next time. Any questions?
Excuse me.
Yes.
While drawing the transverse waves in optical and acoustic mode, you drew two transverse waves, which is what we got. But what about the phase? Like there are different. Like, is there a reason you draw this as outer phase and that as in phase?
What do you mean outer phase?
For example, if it is going up, this is going down for
Yes.
A and B.
It's optical. Optical means they have the opposite displacements in the cell. This is a definition of the optical. Acoustic will have in the same direction, but they might be
sorry,
different.
sorry.
Yeah. No, it's very good. It's a huge amount of information, but if you go slowly, it all makes sense. It's not.
I mixed it up with something else.
Sure, no, but it's really a lot of new stuff. And if you haven't done this before, it takes a while to kind of absorb it. Oops.
Yes.
Yeah. Any questions? Huh? So, if you want, we can stay to solve